Hey everyone, so you're given with this resistor ladder network where all resistors are 1 ohm in value, so that's 1 ohm, and we are asked to find the equivalent resistance of the network. So let's begin by looking for resistors which we can combine to simplify our diagram. So from the get-go, we can see that these bottom two resistors here are connected in series. So you can just get their sum to get their combined resistance. And simply since they are 1 ohm in value, we can get that 1 plus 1, we're going to have a 2 ohm combined resistance for those two resistors. Next, what more can we combine in series and in parallel? Now this one is not so obvious, but this diagonal resistor here can be redrawn to be parallel or vertical with respect to our 2 ohm combined resistance here. Why? Since there's no resistor here and there's no resistor in this space here, essentially, if we redraw it as a vertical connection, we're going to get the same effect. So we're going to place that diagonal resistor vertically, so that's a 1 ohm resistance there. Now, for parallel circuits, we get the sum of their reciprocals and raise that to -1 to get our combined resistance for the combination. So that's 1 plus 1/2 raised to -1. We're going to get a value of 2/3 ohms. Okay, let's remember that it's in 2/3 ohms, and we can redraw the circuit to have our 2/3 ohm combined resistance here. So it's 2/3 ohms. Now, what more can we combine in series and parallel? This? No. These? No. So now we don't have obvious parallel and series connections between our resistors. So when that happens, we can move on to looking for T or Y and delta or pi connections. And you can see here, we have delta connections here and a T connection here. So we can start with this delta here. So let's just redraw our transformed Y connection here. So these are all 1 ohm in value. And let's just have that here. So we have the new and transformed Y connection there, and the previous delta connection of all 1 ohms around it, just so that we can follow through our solutions. So these are all 1 ohm in value and 1 ohm. And let's just label our new resistors here as R2. We can have this as R1 and R3 for that resistor. Now remember our delta to Y transformation formula, which is if we're getting the resistance for R1, we're going to multiply its adjacent resistors all over the sum of the resistors around the Y connection. So that's 1 times 1 over 1 plus 1 plus 1. So we get an R1 of 1/3 ohms. Now by observation, we can see that all of these resistors are equal in value. Thus, it's going to be 1 times 1 over 3 for R2 is going to be 1 times 1 over 3 for R3. So their values are essentially going to be equal to each other, which is 1/3 ohms. Okay, so let's just plug that into our new circuit. So let's just remember that all of them are now 1/3 in value. So it's going to be, just erase the previous connection here, erase that, and we're going to be left with the delta connection. I need the Y connection here, all 1/3 ohms in value. Okay, so you can see that these two resistors and these two resistors, okay, so this is a 1 ohm resistor, are connected in series. So you can combine these two to get a sum of 1/3 plus 1, we get a sum of 4/3 ohms. And for this 1/3 plus 2/3 ohm resistors, we just get a sum of 1 ohm. So the combined resistors and how they will look redrawn in this circuit will be like this. Okay, so we have our 4/3 ohm resistor here, the 1 ohm resistor combined from our previous diagram here, and the 1/3 resistor here, which we got from our Y transformations. So now, again, we don't have any obvious series and parallel connections, so let's move on to our Y transformation. So you can see that this is a pi connection, so we can make a new Y connection here. Okay, so let's just move this 1/3 ohm there, and a redrawn circuit for a Y connection here. Okay, so these three, 1 ohm and 1 ohm in resistance. So these three we can just redraw here for a bigger and clearer picture. Let's just label this with R1, R2, and R3. The 1 ohm resistor here, and the 4/3 ohm resistor, and the 1/3 ohm resistor here. So again, let's go back to our delta to Y transformation formula, which is adjacent times adjacent all over the sum of the surrounding. So for R1, that's adjacent times adjacent, 1/3 times 4/3. Okay, let's just draw parentheses so that it's clear. And all over the sum of this resistances around the Y connection, so that's 1 plus 1/3 plus 4/3. In calculating this, we get a value of 1/6 ohms. And for R2, we apply the same procedure, which is adjacent times adjacent, so we're just going to have 1/3, and we're going to get the sum of these surrounding resistances. That's going to give us a value of 1/8 ohms. And finally, for R3, adjacent times adjacent, 4/3, all over 1 plus 1/3 plus 4/3. And for R3, we are going to get it. Okay, so for R3, we're going to have a value of 1/2 ohms. Now that we have all our values for R3, R2, and R1, we can plug these values into our now transformed Y connection. So let's just erase this first, and we're going to redraw our circuit. Let's just erase these from our delta. Now we're going to be left with this Y connection. Okay. Okay, so we can stick to this, but we can have a clearer and better picture if we follow this. Okay, so we're going to have our values of the 1/6 ohm here, the 1/2 ohm from R3 here, and finally the 1/8 ohm resistor there. Now you can see that these resistors are connected in series, and so are these resistors. So we can just combine these with 1 plus 1/6, that's 7/6 ohms, and 1/8 plus 1, that's just going to be 9/8 ohms. So let's just redraw that when we combine the series connections. Okay. So here we're going to have our 7/6 ohm combined resistance and our 9/8 ohm combined resistance. And again, we can see that they are connected in parallel, so it's an obvious connection. So we just get the sum of the reciprocals and raise that to -1 to get our combined resistance for these parallel resistors. So that's 8/9 plus 6/7 raised to -1. And we get a weird fraction of, okay, it's a pretty weird fraction. That's 63/110 ohms. Now all our resistors are connected in series, so we can easily calculate for our equivalent finally by getting the sum of these four resistors. So that's 1 plus 1/2 plus 63/110 plus 1, and that's going to give us a value of 169/55 ohms. And we can approximate that to 3.07 ohms. So that is our equivalent resistance for the original resistor ladder network. So that is all. Thank you.
So find the equivalent resistance at terminal A and B of the circuit. So I already wrote all the solutions in this problem to save for save sa time. So kani siya nga circuit, makuha na po nato ang equivalent resistance by solving it in a simple way, but we can also use another method, which is the Y delta transformation. We can apply Y delta transformation if there is a pi network, T network, and so on. And in this given circuit, makita ta og pi network, which is this area. So we will cut this part into diagonal before we transform it into a Y delta. And now, since we already transformed it, we put Y labeled A, B, C, which is 20 ohms, 12 ohms, and the 30 ohms. So we can calculate the resistance of each resistors. So in Y delta transformation, we are using the formula adjacent times adjacent over the overall resistors, or the three resistors. And so we will start with C, part C, where we can see that the adjacents are the 12 ohms and the 20 ohms. So here, 12 ohms times 20 ohms over 12 plus 20 plus 30 ohms is equal to 3.87. At A, we can see that the adjacents are 20 and 30, which is, when we multiply and divide and add, we can get the 9.67. At resistor B, the adjacents are 12 and 30, so we get 5.8. To have a simpler look of the circuit, so we can also, in this part, we can see that resistor C and resistor D can be combined because they are in series connection. So we will add 60 ohms which is given in resistor D, and the 120 over 31, which or 3.87, which is equal to 63.87. 120 over 31 is the resistor C. So we already get all the resistors, so we will redraw it, and we came up like this. This is the value of resistor A, B, and the one that we combined earlier, which is the C and D. So in this part, we can simply add, combine the parallel and the series. So first, we redraw it again. We can see that this 2 is parallel to each other, so we get its resistance by this formula, and we get 5.32. So we redraw it again. We can see that 5.32, we inserted the 5.32 in here, and we can see that this 3 is now in series, so we can simply add up the 3 and get 25 ohms. So since this is equal, these 3 resistors is equal to 25 ohms and is now parallel with this resistor here that has a value of 25 ohms, so we will add the 2 inversely and get 12.5 since it is parallel. So as we redraw it again for getting the final answer, this is the 12.5 that we get, and the given 5 ohms and 15 ohms. So in this kanang makita na to na it is in a series connection that we can simply add up to get the equivalent resistance. So 5 ohms plus 12.5 ohms plus 15 ohms is equal to 32.5 ohms. So the equivalent resistance at terminals A and B is 32.5 ohms. So this is the given circuit in number 3, and we are asked to find the IL, or the full load current of the circuit. So we can see that we are already given resistors and the directions of the current, and we can also see that the circuit are short circuits, so the voltage of all the nodes are equal. So voltage are equal at all nodes. The nodes here, given na mga klaro na Japan siya. So let's say that this is A, this is B, this is C, D, E, and F. So the method nga atong i-use is the nodal analysis. In a circuit, we must have a reference node nga connected sa tanan, and the voltage will be at 0. So I'll choose putting the reference node the ANI. This is the reference node, which means nga V is equal to 0 di at dapit. And let's assume that I1, mag-assign na ta sa mga currents. Let's assume that I1 is this, in this part, going into the node B. So the direction of the current is going upward. So let's assume nga muna siya si I1. Since lisod man i-identify ang exact nga direction sa current, in example sa I2, I3, so ma-assume ta nga padulong dito tanan ang current sa node F since ato man gipangita is IL. So can be pwede ning ang I2, I3, and I4. Paubos si I4 since given naman siya. I4, I5, I6. Paubos gyapon si I6 kay given. I7, I8, and I9. So, you can say na I4 is equal to 3ix and ix is equal to I8. So si I4 is equal to 3I8 and I1 i-convert na to. I1 is equal to 6mA, or if i-amperes nimo mahimo siyang 0.06 amperes. I6 ato sang ipangkuan ang mga given. I6 is 3 milliamperes or 0.003 amperes. So we are needed to find the I9 or IL. I9 or IL. So we will use the formula nga I is equal to V over R, or the high potential voltage minus the lower potential voltage over the resistance source. So to find the voltage and the values of the currents to be able to arrive with the full load current nga IL, we will use or apply the KCL to each nodes. So first, atong identify at node B. Ang sa node B, since ang I1 is pasulod sa node B, I1 is equal to I2 plus I3. And I1 is given by 0.006 and I2 is high potential voltage minus R plus I3. And we know that the resistance nga na-connect kang I2 is the kaning 6 kilo ohms or 6,000 ohms plus I3 6 and node B. Later so we simplify V 6,000 plus I3. So later on ato na siyang gamiton to substitute para makuha ang mga values. So sunod, diri na sad ta sa node C. At node C, we can I3, si I3 kay pasulod kang node C, so I4 is equal to I5. And ganiha nakuha na to nga I4 is equal to 3I8 plus so I5 nanatay I3. Next is sa node T. Makita na to nga ang nipasulod kang node T is I5. So I6 plus I7. 7. So ang I6 kay given na siya given which is 0.003. So copy I7 ng I5. So nanata. Ito na punta kang node E. So node E. Node E. I7 ang pasunod kang node E is I7. So A is equal to we can see that, diba, short circuit. So the voltage of node E and node F is just equal to each other kay short circuit man siya. So I8, so VE over I8 kay given na iyang resistance which is 2,000 plus I9 which is given na 3,000. So simplify na to, may mo siyang 1,200. So we have this values, this, and this. So mag-start na din ta substitute. So mabalik ta kang node D. Node D is equal to I5 0.003 plus I7. Since na nakakuha ta diri I7, ato yung i-substitute 3 plus V100 and we'll calculate. So we will now calculate. The answer is 3.6 plus V over 1,200. So we already have I5. So ato na sa siyang i-substitute sa kang node C. Let's go back to node C. I3 is equal to 3I8 plus I5. So since nakuha na to diri kang I8 nga I8 is equal to voltage of E is over 2,000, ato siyang i-substitute tani VE 2,000 plus I5 na atong nakuha diri which is 3.6 plus V and 2,000. We will simplify 3V over 2,000 plus 3.6 plus V over 1,200. Now calculate. So we have 5,600 V plus 7,200 over 2.4 times 10 to the power of 6. So we already have I3. Then, mabalik na sad ta kang node B since I3 here is unknown and we already identified the I3. So, let's go back and substitute node B equal to 0.006 V over 6,000 plus I3. So, V 6,000 plus 5,600 V plus 7,200 over 2.4 times 10 6. So we will get the voltage by calculating this. 6,000 so we now get 1.2 V. So as I said kanihang, this is a short circuit tanan. All voltage is equal to all nodes. So at nodes A, B, C, D, E, and F, the voltage is equal to 1.2 V. So now, kay ang missing na to is, ay ang atong i-identify is si IL man, or the full load current. So, ato sang ipang ko ng unknown. Ang nabilin is, diba Ix is equal to I8 and I8 is equal to this, and 1.2 man atong given nga V over 2,000. So Ix is equal to 6 times 10 negative 4, and IL is equal to I9. I is equal to V over R. So I9 is V over 3,000 since given man ang resistance sa IL. This is 3 kilo ohms or 3,000 ohms. And ang ako na itong voltage is 1.2. So 1.2 over 3,000. 1.2 3,000 is equal to 4 times 10 negative 4. So ang atong IL is 4 times 10 to the power of negative 4.
Now we're going to solve for this circuit diagram we're given here with one dependent source that is a current controlled voltage source, and with two source voltages and 4 resistors connected in series. And in this problem, we are asked to find for the value of Ix here, that's also here, and the power in the dependent source. And we're going to find out whether it's power absorbed or supplied by the dependent source. So the sign of the power in our calculations later will determine whether our source is absorbing or generating power. So the first step is to combine all resistors to get our equivalent resistance. So this should be easy since all of them are connected in series, so we can just add 4 plus 6, that's 10, plus 10 plus 10, we get a combined or equivalent resistance of 30 kilo ohms. So don't forget, this is in kilo ohms. The next thing we can do to just simplify the circuit first is combine our independent source voltages. Now, we can first redraw that as, okay, so we have the negative and positive terminal of the 60 volt voltage here, connected in series to our 20 volt source. Okay, so they're connected in series. Let's just give these positive and negative signs, and by KVL, so okay, Kirchhoff's voltage law, we're going to apply that here, and let's assume that these two have a total voltage here. We're going to get that we have a negative 20 volt plus 60, and don't forget to add this V into our equation, so let's get that 0 by KVL, and by transposition we get 40, we get V equal to negative 40. But we know that we can't have a negative voltage, so we can apply passive sign conventions. So let's just redraw a combined voltage here. It's positive. And here we have positive, negative. We have our negative 40 volts. Here, we know by passive sign convention that negative 40 volts is equal to 40 volts if we reverse the polarity. So if we reverse the polarity in the battery and the source, okay, so positive and negative there, that is just equal to positive 40 volts. Here, have these two. And now let's just redraw our circuit diagram with our combined voltage and our equivalent resistance. So, okay, so let's just redraw that circuit. We have our negative at the top, positive terminal at the bottom, 40 volt source here, connected in series to our equivalent resistance of 30 kilo ohms, connected in series again to our dependent source, positive, negative here, that's 2000 IX. Okay, this is a current flowing IX in the clockwise direction. Now, let's look for equations we can derive from this circuit. We can start with a formula for IX, which is by Ohm's law, VIR, and by transposition, that's I is equal to V over R. So it's going to be our first equation here. So V over R would be of V sub X, and assign polarities here, V sub X. So that's V X over the equivalent resistance, 30 kilo ohms. So that's 30 times 10 raised to 3 ohms. So that is our first equation. Now, next, we can apply Kirchhoff's voltage law in this diagram, and we can start with a clockwise direction. Okay, so we go in this direction. So by KVL, we get 40, since we're entering the positive terminal, so that's 40, plus Vx, positive terminal again, and again positive terminal, so all positive signs of 2000 Ix equals 0. And let's just make this an equation for Vx, so that's going to be Vx equals negative 40 minus 2000 Ix, so this can be our second equation, so that's Ix there. So we can now plug the values of v sub x to our first equation. So that's what we're going to do. We're going to substitute equation 2 into equation 1. So that's what we have here. Ix equals vx, so that's negative 40 minus 2000 Ix over a 30 times 10 raised to 3 ohms resistance. So that'll be equal to negative 40 divided by 30 times 10 raised to 3. We get a negative 1 over 750 value minus 2000 Ix over 30 times 10 raised to 3. Calculating that, we get a negative 1 over 15 Ix. And by transposition, we can add 1 over 15 Ix to both sides, and that's going to give us 16 over 15 Ix on the left equal to negative 1 over 750 on the right. And multiplying 15 over 16 to both sides of the equation, we get that Ix is equal to negative 1.25 times 10 raised to negative 3 amperes. So that is our Ix for this diagram. Now that we have our Vx and Ix, we can solve for power, which is simply P equals Vx times Ix. So that's going to give us P is equal to 2000 Ix times Ix. So that's 2000 times Ix, which was negative 1.25 times 10 raised to negative 3, times another Ix, so that's times 1.25 times 10 raised to negative 3. And that is going to give us a power of 3.125 times 10 raised to negative 3 watts. So since it's a positive sign, our power is being absorbed by our dependent source. Okay, so good day everyone. In this problem, we're given with a circuit with two dependent sources, a battery voltage, and two resistors. And in this problem, we are asked to find, so the required value for this problem is V1. And we can see that variables V sub 1 are in these two components. So the first step is to label the polarity for this resistor. We can choose any polarity we want. We're going to go with this one since it's coherent for the positive terminal and the positive terminal here. Now we can look at the circuit and see that we can solve this problem by Kirchhoff's voltage law. So we can draw a loop here in this direction, clockwise, and you can see that from this battery voltage, a current I will be flowing to the circuit. And in here, in this component, we can make an equation for V sub I as Vi is equal to IR, which is this I here, times our resistor. So that's IR, that's 4 kilo ohms times I. Now going back to this loop, we can make an equation 72 minus 2 kilo ohm times our current I minus 0.5 Vi, V1, 0.5 V1 is equal to 0. Now we have a V1 here. We want to have an equation with only one variable, so we can go back to the equation we made here and substitute to plug it into our equation. So that's 2 times 10 raised to 3. Let's just copy everything with now the substitution we made for V1 here, V1. So that's times 4,000, okay, 4 times 10 raised to 3 times I is equal to 0 by KVL. Now, when we combine these two, we are left with a -2 minus -2. So it's -2 minus 2. We're left with 72 minus 4 times 10 raised to 3 I equal to 0. And by transposition, we get that I is equal to 0.018 amps. Now we are asked to find V1. We can plug this value of I into our equation. So that's V1 equal to 4 times 10 raised to 3 times I, and we have I here, so that's times 0.018, which gives us a value of 72 volts. So that is the value of V1 in this circuit diagram, which is just equal to the voltage.